This is the first video in a series that will cover a basic course in Lie Algebras. So we'll start with some basic definitions and examples, move into representations of Lie Algebras, and then after that we'll prove a nice classification theorem involving Lie Algebras. Okay, so let's jump right into the definition. So let's suppose that F is a field. Generally, we'll take F to be the complex numbers, although sometimes we'll take it to be something else. So a Lie algebra L is a vector space over this field together with a bilinear map known as the Lie bracket. And so that takes two elements from L and gives us a new element from L. And the notation is this right here. And it's got to satisfy a couple of conditions. So for all x, y, z in L, we have to have this alternating condition that if you bracket x with itself, you get 0. And then we've got this other condition that controls how non-associative this operation is, which I guess I should point out that Lie algebras are a class of non-associative algebras. So we have this so-called Jacobi identity. So we've got the bracket of x with the bracket of yz plus the bracket of z with the bracket of xy plus the bracket of y with the bracket of zx is equal to 0. So let's jump right into our first little result before we look at some examples. And that will be if the characteristic of f is not equal to 2, then this first alternating condition can be replaced with the following condition that says bracket yx is equal to negative bracket xy for all xy in L. Let's recall that the characteristic of a field is the number of times that you can add, 1 to itself and get 0. So if you've got a field with characteristic 2, that means 1 plus 1 is 0. So for instance, z2. And so we say that a field with infinite characteristic actually has 0 characteristics. So the field of rational numbers, complex numbers, real numbers, those are all characteristic 0. Okay, so anyway, let's get into this calculation, and it's pretty straightforward. We'll simply start with the left-hand side here and work towards the right-hand side. So we've got bracket yx. Well, that's going to be the same thing as the bracket yx minus 0, and we're going to write 0 like this. We'll write it as the bracket of xy with itself. Using this fact over here that the bracket of xx or the bracket of anything with itself is 0. Okay, so now let's maybe see where that takes us. So that'll give us the bracket of x or yx minus, well, expanding this out, we'll get bracket xx minus bracket xy minus bracket yx minus bracket yy. Great. And so that's just like foiling everything. But let's see, does some stuff cancel? Well, in fact, it does. So this bracket xx and this bracket yy cancel from the alternating condition. And then let's see, this bracket yx and this bracket yx cancel because they're attached to two different opposite sign numbers, 1 and -1. This collapses to negative bracket xy. So let's see, have we done it? Well, we started with bracket yx and we ended with negative bracket xy. So I guess that maybe proves one direction, and that is that this condition right here implies this condition. But now let's maybe try to prove the other direction. That's actually pretty straightforward because if we take bracket xx, so maybe let's put here, on the other hand, meaning in the opposite direction, bracket xx, that's equal to negative what we get if we switch the entries here. But swapping the entries, we get the same thing. So we get negative bracket xx. But now let's notice that that means that bracket xx plus bracket xx is equal to 0. But that can only hold in a field of characteristic 2, because that's got to hold for all vectors x inside of the Lie algebra. But now putting this together, we see that this means that 2 bracket xx equals 0. So that means either 2 is 0, which means we're in a field of characteristic 2, which we assume that we are not, or the bracket x, x is 0. And that bracket xx is 0 for all vectors x. Well, that means that in fact, that's what we have. We have bracket xx is indeed 0. But that's exactly where we wanted to end in this opposite direction. So for our first example, we'll take the so-called general linear Lie algebra. So we'll denote it by this fancy GLNF. And so F is the field that we're working with. So this could be C or R or maybe a finite field. And this is all going to be all n by n matrices with entries from this field. And then we take the bracket to be, well, what's sometimes called the commutator. So bracket AB is AB minus BA. And now let's check that these two conditions are satisfied. The first one is really straightforward. So notice this turns into a squared minus a squared, which is equal to 0. So in fact, yes, this is alternating. And now let's unravel this second condition, this Jacobi identity, a bit at a time. So this will be bracket A with BC minus CB, expanding out this bracket BC. And then that'll be plus bracket of C with AB minus BA. And then finally plus bracket of B with CA minus AC. Great. And now let's apply that again. So this first one will give us ABC minus ACB. So that would be A multiplied into it from the left. And then we'll subtract off BCA and then plus CBA, where I distributed a minus sign through. So there's multiplying A through on the left and multiplying A through on the right. And now let's see, for the next bit, I'll have plus CAB minus CBA, and then let's see, minus ABC plus BAC. Great. And so that'll be, like I said, for the second one. And then for the third one, I'll have plus BCA minus BAC, and then minus CAB, and then plus ACB. Okay, great. So let's see if everything cancels. Well, obviously it should, because I'm saying that this is an example of a Lie algebra. Okay, so let's see. ABC we have here, and there's a negative ABC. So those two cancel each other. Now we have ACB here, and then we've got an ACB down here, so those cancel each other. We have a negative BCA here, and we have a positive BCA here, so those cancel each other. Here we have a CBA, and here we have a negative CBA, so those cancel as well. And then let's see, here we have a CAB, a negative CAB, those cancel. And then finally, we have a BAC and a negative BAC, so those cancel. So everything cancels down to 0, which means the Jacobi identity is satisfied, which means we indeed do have a Lie algebra. Okay, let's look at another example. Okay, so for our next example, this is actually a subalgebra of the GL2, but we haven't defined a subalgebra yet, so we'll just look at it as a Lie algebra on its own. So it'll be SL2C. And put very shortly, it's everything in GL2 that has trace 0. But what does trace 0 mean? Well, the trace is the sum of the diagonal, so we need the sum of the diagonal to be 0. So here's it out like expanded a bit. So we've got a 2 by 2 matrix, ABCD, such that A plus D is equal to 0. Okay, so by standard linear algebra techniques, we can see that SL2C has the following basis. So I'll say that it's spanned by E, F, and H, where E is the matrix 0, 1, 0, 0, F is the matrix 0, 0, 1, 0, and H is the matrix 1, 0, 0, negative 1. So again, you can find that from simple linear algebra techniques. But now let's check the bracket of those. So the bracket is the same as we had before, so it's the commutator. So we already know that it satisfies this alternating condition and this Jacobi identity. We really just have to check that, our subset, or really our subspace, our vector subspace of GL2 is closed under this operation. Okay, so let's do some calculations. So let's do H with E. So that's going to be HE minus EH. So writing this out, we have 1, 0, 0, negative 1, and then 0, 1, 0, 0 minus 0, 1, 0, 0 times 1, 0, 0, negative 1. So let's see what that does. So multiplying this in, we have 0 here, and then we have a 1 here, and then we'll have zeros in these entries. And then multiplying that in, we actually get, let's see, minus a 0 here, a negative 1 here, a 0, and a 0 here. But notice those minuses cancel, leaving us with 0, 2, 0, 0. In other words, 2e. So that means that e is something like an eigenvector of this bracketing action with h with eigenvalue 2. That'll be something important that we see, a bit later. Okay, so now what about h with f? Well, you can do a very similar calculation, so maybe I won't work through it, but you end up with minus 2f. The important thing is that you're back inside of the subspace. And then I guess there's really only one left, and that would be e with f. And I say there's only one left because we can get all of the rest of them using, the alternating rule, or the fact that EH will be minus HE, and so on and so forth. Okay, so EF, you can actually calculate that to be H. Okay, great. So notice it's closed, or this space is closed under the bracket, but that's going to make it a Lie algebra. Okay, let's do another. So here's another really important class of examples, and it requires a little bit of a definition. So let's say that we're given an algebra A and a linear map D from A to A. So that's like a linear transformation. So this linear transformation is called a derivation if it satisfies this rule. So d of A times B is equal to A times d of B plus d of A times B. So that looks like the product rule from calculus, which gives us a reason for calling this a derivation. So the result here is that der A, in other words, the set of all derivations, is a Lie algebra with the bracket, which is just the commutator. So notice a lot of things we don't need to check. For example, we don't need to check these two conditions over here because those conditions hold for all linear transformations, pretty much using the same method we used for the matrix example. So what do we need to check? Well, we need to check that this is in fact a vector space. So in other words, if you take linear combinations of derivations, you get a derivation. I'm going to leave that to you. That's fairly straightforward. Another thing that you have to check, which is maybe the most important, is that if d1 and d2 are derivations, then the bracket of d1 and d2 is also a derivation. So in other words, derivations are closed under this bracket action. Okay, so let's check that. And we'll do that by taking the bracket of d1 and d2 and plug in AB and show that it satisfies this green boxed condition. Okay, so let's expand this out a little bit at a time. So this is going to be d1 operating on d2 operating on AB minus d2 operating on d1 operating on AB by the definition of our bracket. And now let's just move from the inside to the outside carefully. So this is going to be d1 operating on, let's see, A d2b plus d2a times b. That's using the definition of d2, or I guess not the definition, but the fact that d2 is a derivation. And then here we'll have minus d2 operating on a d1b plus d1a times b. Great. And now remember, a and b are elements of the algebra, so we can't factor them out really. But we can use the fact that we have linearity here to split up the plus. And maybe while we do that, we're going to apply the fact that d1 and d2 are derivations again. So we'll need to do d1 acting on a times d2b, and so on and so forth. So let's see what that leaves us with. That'll leave us with a d1 d2b plus d1a d2b. So that's this bit right here expanded out using the fact that d1 is a derivation. Then we're going to have something similar for this over here. So that'll be plus d1 d2a plus d2a d1b. Again, that's this expanded out using the fact that d1 is a derivation. Now we're going to do the same thing over there. So this will be minus, let's see, a d2 d1b, and then minus d2a d1b. So that's this bit expanded out using the fact that d2 is a derivation, and then minus d2 d1a minus d1a d2b. Again, this expanded out for the same reason d2 is a derivation. And now let's start canceling things. So let's see, we've got d1a, d2b. Do we see another copy of that with a minus sign? Yes, we do, way over here. So this term will cancel this term out. Then let's see, we have a d2a, d1b. Do we have another one of those? And we do, we have it right here. So those two cancel out as well. And then let's start putting some stuff together that's left over. So let's take these two. Notice they both have an a out front. We can factor the a out of the left. And then let's take these two, which should have had a b on the right. So let's insert that, and we'll factor the b out of the right. So let's see, that'll leave us with a times d1 d2b minus d2 d1b. But notice that's exactly d1 bracket d2 evaluated at b. And then factoring a b out of the right, we get exactly what we want. So we'll have the bracket of d1 d2 operated on a times b for essentially the same reason. Okay, so just to reiterate, this we got from these peach underlined terms, and this we got from the blue underlined terms. So we've done it. We've shown that if we bracket two derivations, we get a derivation. And then, like I said, all of the other things kind of come for free or come very cheaply. So that's all we really needed to fill in to show that derivations of an algebra form a Lie algebra. Okay, let's look at a special case of this, broader family of examples. Now let's look at a special case of that family that we just talked about. And that's this thing called the Witt algebra, which is the derivations of Laurent polynomials. Laurent polynomials are polynomials where you allow for positive and negative exponents on the variable. And I've got a video where we derive this basis on the main channel if you'd like to check it out, but we'll take the following form of the basis. It'll be the span of these things that we call Ln, where Ln is minus z to the n plus 1 times the derivative with respect to z. So let's find the bracket relations on these L's. Okay, so let's just write it out. So we've got minus z to the m plus 1 derivative with respect to z, minus z to the n plus 1 derivative with respect to z. So let's see, that minus signs will cancel, and we'll have z to the m plus 1, the derivative with respect to z of z to the n plus 1 derivative with respect to z. So that's from the first bit. And the second bit will give us minus z to the n plus 1 derivative with respect to z, and then z to the m plus 1 derivative with respect to z. But now let's use the product rule to take these derivatives here. So we need to take the derivative of the power of z and take the derivative of the derivative, building it up to a second derivative. So this first term expands out a little bit. So let's see, we'll get n plus 1 times z to the n times the derivative with respect to z. That's from taking the derivative of the z to the n plus 1. And then we'll have plus z to the n plus 1, the second derivative with respect to z. And then we've got a similar thing for the other bit. So that'll be minus z to the n plus 1, and then we'll have m plus 1 z to the m, and then plus, let's see, z to the m plus 1 times the second derivative with respect to z. But let's notice that those second derivatives with respect to z are attached to the same term. They're attached to z to the m plus n plus 2. So that means this and this cancel each other. But then what does that leave us with? I forgot my derivative with respect to z here. Well, that leaves me with something like this. We have minus m plus n, sorry, that should be minus n, times z to the, let's see, m plus n plus 1 times this derivative operator. So that's just from all this simplification. But what is that? That's exactly m minus n L of m plus n. So there's our rule. There is our bracket relation on the basis elements for this wit algebra. Okay, let's look at another example. So our next example is another super classic one, and that is three-dimensional vectors. We'll take them over the real numbers together with the cross product. Let's recall that the cross product is defined as follows. That gives us a vector which is perpendicular to the starting vectors. So just based off of this formula right here, it's pretty clear that if you cross product a vector with itself, you get 0. Then how do you check the Jacobi identity? Well, I think the simplest way is to prove the following relation involving the cross product. So we've got u cross v cross w is equal to u dot w times v, so scalar multiplied into v, minus u dot v w. And then once you have this, the Jacobi identity is pretty straightforward. I'm going to leave that as an exercise though. So another way at arriving at Lie algebras is as the tangent space to a Lie group at its identity. So we're not going to look at this so much, but I'd like to at least present an example of this happening. So the idea is that you start with a group G, which is also a smooth manifold. You also need the group operation to be differentiable and all of this kind of stuff. This is called a Lie group. So a lot of your favorite classical matrix groups are Lie groups. And then G, the tangent at the identity of this group, in other words, it's like a plane or a linear version of the group. This is called the corresponding Lie algebra. So let's work through an example, but like I said, we're not going to work much with the Lie groups. We'll almost only be working with the Lie algebras in the future. Okay, so let's take capital SL2C. So those are going to be all 2 by 2 matrices with determinant 1. And then let's take a curve, and I'll call this curve gamma. And so it is parametrized, or maybe it's parametrized by gamma. So it goes from R into SL2C. And it is such that gamma of 0 is equal to the identity. In other words, it's 1, 0, 0, 1. And now we want to show that the tangent to this curve at 0, in other words, at the identity, is in the Lie algebra that we talked about before. And this is actually not so hard. So let's take gamma as the following maybe matrix. So it's the matrix where we have A of t up here, B of t up here, C of t up here, and D of t here. So if we're going into SL2C and we're parametrizing, that means all of those entries could be changing. And then what do we know? Well, we know that A of t, D of t, minus B of t, C of t equals 1. And that's going to be true for all values of t. That's because we're in SL2. We also know that A of 0 equals D of 0 equals 1, and B of 0 equals C of 0 equals 0. That's because we're at the identity at 0. And now let's take the derivative of this equation right here. So we'll get 0, because 0 is the derivative of 1, is equal to the derivative with respect to t of, I'm just going to write this as AD minus BC. I'll leave off the dependence on t for the moment. But now using the product rule and such, we get A prime D plus AD prime minus B prime C minus BC prime, and then that's it. And now we're going to evaluate this at t equals 0. So evaluating this at t equals 0, notice these two terms cancel. That's because we get a C of 0, and we also get a B of 0. And those are both 0 from this condition right here. And then D of 0 is 1, A of 0 is 1, so that gives us A prime, I'll write it as of 0, plus D prime of 0 equals 0. So in other words, the trace is equal to 0. But let's also recall that this element gamma prime of 0, which is equal to A prime of 0, B prime of 0, C prime of 0, D prime of 0, is by definition inside of this Lie algebra, because that's in the tangent space at the identity based off of how we took this curve. So by the tangent space definition, this thing is inside of the Lie algebra, but then because of this determinant 1 condition, we see that the trace is equal to 0. So what we've shown here is that if something is inside of the Lie algebra, then its trace has to be equal to 0. And then you can show the vice versa as well. And that's the explanation for why we took SL2C, the Lie algebra, to be trace 0 matrices, because of this sort of rule right here. Okay, I'm going to leave you with some exercises. Here are 4 nice exercises. So the first is to check all the details that R3 with the cross product is a Lie algebra. The second starts with a little bit of a definition. So a Lie algebra is abelian if bracket xy is equal to 0 for all x, y. And then show that every one-dimensional Lie algebra is abelian. Next, let's say that Eij is the matrix with all zeros except for a 1 in the ith row, jth column position. And then check the following commutation relation on Eij, Ekl. So delta jk, well, that's the standard rule that that's equal to 1 if j is equal to k and 0 otherwise. Next up, let's consider the symplectic group SP4. So that's going to be all 4x4 matrices such that A transpose JA is equal to J, where J is this matrix with like identity matrices on the off diagonal, this one negative. So that's a 2x2 identity matrix. And then use the method that we used in the previous example to show that the corresponding Lie algebra satisfies the following rule. So X is such that Jx minus X transpose J is equal to 0. And that's a good place to stop.